Environmental Stress on Heart Rate by Elise Crawford Paz Solden, Emily Shin, Reagan Mills, and Cameron Katadani. Does environmental stress impact heart rate? The articles discussed in this video presentation look at if heart rate changes with different environmental stresses, such as pain, sleep, anxiety, and fear. To begin, we will examine pain. An article by A. Moltner entitled Heart Rate Changes as an Autonomic Component of the Pain Response seeks to answer this question. This study asks, does pain cause changes in autonomic responses of the body? It is hypothesized that pain affects autonomic responses such as heart rate change. As pain stimuli increase, it is predicted that the autonomic response of heart rate will also increase. Previous investigations of pain stimulation have used mainly aversive sound or weakly defined pain stimulation. However, this study used a distinct and different method of pain stimulation, which was the application of heat. This study involved 12 healthy subjects who gave their informed consent. A cutaneous heat stimuli was applied to the subject's right hand using a Marstock thermode, with the semisphere for the subject to determine their pain threshold. The stimuli was then introduced in phases to the subject starting at 37 degrees Celsius with a constant heating rate of 2 degrees per second. The subject then rated the stimuli on a 9-point scale from no sensation to very painful. The heart rate was then measured as the pain stimuli was given using a cardiotocograph coupler with a chest lead. There were 3 different methods of evaluating the heart rate response. First was a classification of the distinct heart rate patterns. This method looked at the average evoked heart rate responses over 3 temperature classes for each subject. Second was the amplitude and latency, or delay, parameters of the different heart rate patterns. Third was the differential temporal relations of the early and late response types, which was compared to the intensity of the pain stimuli. The results for the first evaluation of heart rate showed 2 types of average evoked heart rate responses, monophasic and biphasic. Monophasic is represented by a heart rate pattern with 1 peak, and responses had an increase of about 8 beats per minute. Biphasic is represented by a heart rate curve with 2 peaks, and responses had about the same magnitude as monophasic responses. The differential temporal relation results found differential time-dependent correlations with stimulation temperature, but also the perceived intensity of the stimulus of heat by the subject. Overall, the results showed a mean heart rate increase for stimulus intensity classes. The results also showed a correlation between temperature and mean heart rate increases. When the temperature increased, the mean heart rate also shows slight increase in general. The mean heart rate increase after stimulation showed a positive relation to stimulation temperature. However, there was also a relation with subject ratings and the delay before heart rate response, indicating that autonomic responses to heat pain stimulation might be from the subjective sensation rather than a direct response to the stimulation. This weakens the relationship found in the results between the 2 variables. Although the relationship is generally weak, it is statistically significant. The first part of the study also showed that characteristic monophasic and biphasic types of heart rate responses could differ, but with no significant dependence on frequency or amplitude and latency measures on the pain intensity. The results found in this experiment are important because they could be important for clinical applications to use nonverbal methods of measurement of different types of pain. As many of you probably know, sleep has an impact on heart rate. In order to find out the actual data of this phenomenon, Frederick Snyder J., Alan Hobson, Donald Morrison, and Frederick Goldfrank all did research writing a paper called Changes in Respiration, Heart Rate, and Systolic Blood Pressure in Human Sleep. This research came about because during sleep, it was previously generally accepted that respiratory rate, heart rate, and blood pressure would all fall and become lower during sleep. However, other researchers found that pulse and breathing of infants would increase and decrease over periods. With further research done by others, Arskensi and Kleitman, Camilla, and Juviet et al. Found data correlating with different phases of sleep. The researchers in this study predicted that they would find data similar to these previous researchers. The hypothesis was that during sleep, heart rate would decrease. For this study, they basically were trying to quantify the relationship between heart rate, respiratory rate, systolic blood pressure, and the EEG patterns of human sleep. but we only really are interested in heart rate for this subject. Methods. The subjects of this experiment consisted of 5 men aged 18 to 23 and 7 females aged 18 to 26. The researchers watched them while they slept for 2 to 6 nights. The subjects of this experiment were hooked up to all sorts of different machinery. But since we only care about heart rate for this presentation, the patient's heart rate was recorded using a photoelectric plethysmograph attached to the right toe. In some cases, the heart's electrical activity was monitored with clavicular electrodes. To make the patients nice and comfy for their sleep cycle with a nice range of motion, the wires were all attached, combined into a cable that was attached to the pajamas, which left them from the bed by the left foot. The subjects were prepared at 11 p.m., and all of them fell asleep between midnight to 1 a.m. Most of them woke up during the first 1 or 2 nights, so recording continued the next few nights until they slept peacefully, which was considered to be 6.5 hours of sleep without waking up for more than 5 minutes. The 5 male subjects each slept for 2 to 5 nights, totaling to 15 nights. The females each slept 1 to 4 nights, totaling to 15 nights as well. To create a control, 3 subjects slept for another 2 nights without the blood pressure machine hooked up to them. Heart rate was counted manually for 30 seconds. The mean and variability index was calculated in each 5-minute sample. The variability index was found with a formula that was basically the average absolute difference of successive intervals. It is shown with this formula here. Heart rates fell 5 to 10% throughout the night from the levels found when falling asleep. The lowest levels sometimes were found during the early hours of sleeping. To make sure that the data wasn't just caused by the time of night, the researchers took data from different times of the night with intervals from the different stages of sleep. This proved that their data was still significant among the different stages of sleep. In this table, you can see that heart rate varied quite a bit, first decreasing, then slightly increasing, as shown with the numbers in the orange boxes. Also through the graph, one can see that the solid bars as outlined in orange show a decrease without much change in the next 2 REM periods. Discussion. The hypothesis of this experiment was supported. Heart rate decreases during sleep. However, the study leaves some questions unanswered, especially those pertaining to sleep depth and respiratory rate as it corresponds to sleeping heart rate. Next, we will look at anxiety. Anxiety. The article Autonomic Dysregulation in Panic Disorder and in Post-Traumatic Stress Disorder, the application of power spectrum analysis of heart rate variability at rest and in response to recollection of trauma or panic attacks, investigates the effect anxiety and other stress conditions have on human heart rate. The experiment sought to answer the question, how does heart rate variability change due to PTSD and PD, post-traumatic stress disorder and panic disorder, both conditions of which physiological anxiety is a key component? Why test this? Previous studies have shown that various stressors, emotional and otherwise, can influence human heart rate. The ramifications of this study have important implications for the medical field and understanding the manifestations of disorders such as PTSD and panic disorders. Understanding how the behaviors which manifest as a response to trauma impact the body's physiological processes is key for the treatment of such disorders. 14 patients experiencing PTSD or PD, otherwise not medicated, were inducted into the study after passing a comprehensive set of screening tests determining eligibility for the study. All patients reported a high frequency of panic attacks, 2 or more within a week. A control group of 25 patients free of panic disorders or PTSD were also inducted into the study. Electrocardiography, or ECG recordings, were used as a measure of heart rate and were taken over 15-minute intervals each time. A baseline was established in which all patients were completely at rest in a stress-free environment. Heart rate was then monitored and recorded using the ECG while patients were instructed to recall a traumatic event or their last panic attack for the next 15-minute segment. The final 15-minute heart rate segment was then taken at rest once again. The results of the experiment are as follows. First, it was determined that PTSD and PD patients had a much higher resting heart rate than the control group. Differences in heart rate and other autonomic responses were not significant for these interest groups, those interest groups being PTSD, PD, and control patients, in the phase of the experiment where they recounted or described traumatic events. This phenomenon is accredited to PTSD patients experiencing something called chronic autonomic overstimulation, meaning their autonomic functions are already elevated consistently and would not dramatically change during panic situations. This experiment predicted that PTSD and PD patients would experience significant increase in heart rate during the recounting of trauma or panic attacks. However, PTSD patients were found to not experience a significant increase in heart rate, while panic attack patients did. This suggests a different physiological and autonomic function of the two disorders. Thus, the findings of the study indicate, tentatively, that a study of heart rate variation between PTSD patients and PD patients may be helpful in distinguishing their diagnosis, although further exploration is required due to the admittedly limited scope of the study. The goal of this study was to determine whether there was a physiological link observable in heart rate variability to the two psychiatric disorders of PTSD and/or PD. The study was able to tentatively conclude that an examination of heart rate variability in response to triggering stressors may be used as a distinguishing characteristic of the diagnosis of the two disorders. Next, we will take a look at heart rate variability and fear. This study examined how fear, anticipatory anxiety, affected HRV amongst a sample of individuals with low anxiety, low resting heart rate, and high resting heart rate. It was predicted that a low HRV will lead to a higher startle potentiation, and that panic patients, along with a control group, would not have differing startle potentiation. The study is relevant because everyone experiences fear, and it is important to understand the factors around it. Two studies were executed to measure the effect of startle potentiation depending on an individual anxiety variable and resting heart rate. The first study was based on the sample's anxiety level, measured through the Anxiety Sensitivity Index by having the sample respond to different tasks that provoke a variety of anticipation symptoms. 22 subjects, 14 female, 8 male, high in anxiety sensitivity, and 21 subjects, 14 female, 7 male, low in anxiety sensitivity were studied, with an average of 23.3 years of age between them. All participants gave consent to the experiment. Electrocardiogram was measured for HRV, and an electromyographic test measured eye blinks. Participants were told that different colored slides, blue and yellow, represented safety, the blue slide being safety, and the yellow slide representing a threat of 1 to 3 shocks delivered to the patient. Participants were shown either a safe or a threat condition with a 10-minute resting period between. Following the resting period, they received the opposite condition. 1 week later, they did the same treatment but switched the order. If a participant experienced the safe condition first in the previous week, they experienced it second in the following week. The second study focused on panic disorders. 9 subjects, 7 women, 2 men, averaging 34.2 years of age, diagnosed with specific panic disorders were recruited, along with 15 control subjects, 7 women, 8 men, averaging 34.6 years of age with no identifiable disorders. Participants were purposely told they could ignore the audio being presented via headphones. An initial baseline HRV was measured based on 8 acoustic startle-eliciting stimuli. The participants were told to ignore it so they don't subconsciously alter their HRV. Light in the chamber alternated between bright and dim lighting every 2 minutes. Startle probes were presented to the participants. This experiment showed no threat, and the participants did not know a threat experiment was to follow. In the treatment experiment, the experimenter told the participants that they may be administered 1 to 3 shocks at any time. No explicit cues were given, contrasting the previous study that had blue and yellow slides. The alternating light treatment was repeated, and just before the end of the light cycle, the participants were delivered a mild electrical shock. The order of experiments for Study 2 were purposely not counterbalanced, because if they were, there might have been carryover effects that could alter the results. For Study 1, shown on the left graph, there was generally no difference between startle response for low and high HRV. However, for the threat treatment, there was a significant result. High HRV participants decreased their anticipation throughout the treatment, whereas the low HRV participants had prolonged anticipation out of fear startle. With the simple attachment of the shock electrode came a general anxiety and anticipation. For Study 2, panic patients experienced a higher baseline startle response as expected. The control group was represented by high and low HRV, similar to Study 1. In comparison to the high HRV control group, panic patients showed a significantly higher heart rate. The elevation from safe to threat between the low HRV participants and the panic patients were not statistically significant. Panic disorder patients had high startle response magnitudes during the threat treatment, where the high HRV participants did not experience much change. The introduction of the threat of shock led to a distinct startle potentiation. In conclusion, both studies support the hypothesis made at the beginning of the experiment. The prediction that panic patients and their controls do not differ was supported, kind of. The panic patients differed from the high HRV participants. However, the elevation differences did not differ from the low HRV participants. Both studies show that low HRV results in a higher startle potentiation, likely because those with high HRV levels are already naturally heightened. The data shows that the difference in elevation from the safe to threat treatment from low HRV participants is equal to that of the panic patients, despite the panic patients having a higher quantitative level. The size of the sample tested shows relative trends, but a larger sample size could have revealed more information. However, resting HRV is an important indicator of the information the study was looking for. This creates the need for research to see if low HRV is related to a higher likelihood for anxiety or panic disorders. In conclusion, this presentation, Environmental Stress and Heart Rate, walked you through the effect of 4 environmental factors on heart rate as demonstrated by the results of 4 scientific experiments. Pain, sleep, anxiety, and fear all affect human homeostatic regulation of heart rate variability. It is important to investigate these factors and their physiological impact on us as human beings because it allows us to improve upon our understanding of the human experience in its biologically quantified form.